Perimeter is another method that takes no parameters and returns a float64. Now, any type that implements both of these methods and matches their method signatures will implement the shape interface, which really just means that we can think of it and treat it as a shape. So for example, let's take a look at this rectangle struct. So a rect has a width and a height, both of which are float64s. And again, this is just a kind of standard struct. And it has two methods on it. One is the area method that takes no parameters, returns a float64. One is the perimeter that takes no parameters and returns a float64. And because a rectangle implements both of these methods, we can think of a rectangle as a shape. A shape is just anything where we can kind of calculate its area and calculate its perimeter. And multiple types can implement the same interface. So for example, this circle struct, it has different underlying data, right? Rather than a width and a height, we can represent a circle with just a radius. But to calculate its area and its perimeter, the calculation is a little bit different, right? We're using pi, for example. But the method signature is identical, right? We don't pass anything in because we have all the data we need on the circle struct, and we just return a float64. So both circles and rectangles, because they implement the required methods, can be thought of as shapes. Or we could say they implement the shape interface. Let's get into the assignment. I think it'll all start to make a little more sense. So the assignment says the birthday message and sending report structs have already implemented the get message method. So let's take a look at that. So birthday message is this struct here. Sending report is this struct here. They both have this get message method that returns a string. And they're just, it looks like the strings that they return are just a little bit different, right? The birthday messages get message function returns this like, hi, blank, it is your birthday on blank. And a sending report says your blank report is ready, right? So they're just formatted a little differently. Okay, so assignment says first add the get message method as a requirement on the method interface. Okay, so we need to finish the message interface and add a get message method that returns a string. Okay, cool. So now this message interface, because birthday message and sending report both implement this method, we can think of both of those as messages. Next, it says complete the send message function. It should print a message's message, which it obtains through the interface method. Okay, cool. So a message is an interface. So inside of the send message function, we don't actually know if we're dealing with, say, a birthday message or a sending report. We just know that we have access to a message. So really the only thing we can do with it is call get message, which we know will return a string. And it says it should print a message. So we'll do fmt.println. We'll just print out the message. Cool. Okay, now this is powerful. Right? Let's go take a look at how this code is actually called. So we have this test function that also just takes a message, and it sends that message, right? It's just calling our send message function here. But down here, and this is where it's most interesting, the test function is not past like interface literals. That's not even like a real thing, right? An interface is like abstract type that represents other types. Instead, because the test function takes an interface, we can pass into it any struct that implements that interface. So, for example, here on line 42, we're passing in a sending report. And then on line 46, we're passing in a birthday message. Those are two different types in a strongly typed language being passed in as the first parameter to a single function. But the reason it works is because we're using interfaces. Okay, let's go ahead and run this, see what happens. Your first report is ready. You've sent 10 messages. Hi, John Doe, it is your birthday. This looks great. This looks great to me. In Go, interfaces are implemented implicitly. And what that means is when we have a type, like in our last example, we had the rectangle type that implemented the shape interface, we never had to explicitly write anywhere on the rectangle struct that it was intended to implement the shape interface. Because it satisfied all the requirements of the shape interface, it just kind of automatically implemented it. And that's fairly unique to Go. In a language like Java, we might have to write something like this. We could take a look at this little example here. We've got this employee interface and a contractor struct. If we wanted the contractor to implement the employee, we would need it to still fulfill the interface, right, by implementing all the methods, but we might need to also explicitly type something like implements employee, right? We'd explicitly say that we intend to implement that interface. In Go, it's done automatically. Let's hop into the assignment. It says, at Textio, we have full-time employees and contract employees. We've been tasked with making a more general employee interface so that dealing with different employee types is a little simpler. Add the missing get salary method to the contractor type so that it fulfills the employee interface. Okay, cool. So we have the employee interface, we have the contractor struct. And if we look at the full-time struct, it looks like it already implements the employee interface. So we just need to add the missing method because right now a contractor has a get name, but does not have a get salary. Okay, cool. So let's go ahead and do that. We'll do employee get salary. It returns an int. And a contractor's salary is their hourly pay multiplied by how many hours they work per year. Okay, so be something like C dot hourly pay multiplied by C dot hours per year. Okay. And just because I'm curious, I want to go look at how a full-time salary employee works. Yeah, so you can see the way that a full-time employee, their salary is calculated is totally different. Like their salary is actually just stored, probably because the way we think of full-time employees is like, you know, you make $60,000 a year, you make $70,000 a year, whereas contractors often get paid by the hour. So it makes sense that they have a different calculation. And then down here in the test suite, this looks very similar to the last assignment where the test function is able to take as inputs any type of employee, right? So we can pass in both full-time and contractors here. Let's go ahead and run that. Jack, Bob, and Jill, we can see all of their salaries, even though Jack is full-time and Bob and Jill are both contractors. So that looks good to me. In Go, types implement interfaces implicitly because it kind of decouples the definition of the interface from the definition of the type. The type doesn't even really need to know that it implements a certain interface. And that's really, really cool because it means it's easy for a type to implement lots of different interfaces. So the quiz question here is, how is an interface fulfilled? Answers are, a type has all the required interfaces methods defined on it, or a struct embeds the interface in its definition. And the answer is going to be, it has all the methods defined. The next question is, can a type fulfill multiple interfaces or implement multiple interfaces? And yes, why not? Another quiz question. Go uses the blank keyword to show that a type implements an interface. And the answers are fulfills, implements, inherits, and there is no keyword in Go. And the answer is that there is no keyword in Go. Interfaces are implemented implicitly. In the next question, it says, in the example given, the blank type implements the blank interface. Let's take a look. So example here, we've got the shape interface, circle struct, circle has an area method. So it looks like the circle type implements the shape interface. Like we talked about before, a type can implement multiple interfaces. It just needs to have all the methods for all of the different interfaces. For example, the empty interface, so that's this definition right here, this is an interface with no methods required, is actually always implemented by every single type in the Go programming language. Now, it's often not a very useful interface because you can't really do anything with an empty interface. You have no methods to call. Let's jump down into the assignment. It says, add the required methods so that the email type implements both the expense and printer interfaces. Okay, cool. So we've got these expense and printer interfaces, two different methods we need to implement. And we have this email type with an isSubscribed Boolean and body string. Cool. All right, cost method. If the email is not subscribed, so if not e.isSubscribed, I believe is what the field was, then the cost is 0.05 times the length for each character in the body. So the length e dot body. Now, remember, Go is strongly typed, and we can't multiply an int by a float directly, so we need to cast this integer. Sorry, I think I highlighted those backwards. The length of the body is an integer. This is a float. So we need to cast the length of the body to a float. So we can multiply a float by a float. Otherwise, we'll return it's 0.01 times that same thing, the length of the body. Cool. The print function should just print to standard out the email's body text. Easy enough. fmt.println e.body. Okay. So now our email struct implements both of these interfaces. And if we come down here to look at the test function, this is interesting. The test function takes an expense and a printer, right? So we can use both of those methods there. And actually, the email struct, so we're creating instances of emails here, we're actually passing it into test as both the expense and the printer, right? Because it makes sense. It implements both. Cool. Let me run that. Oh, what did I screw up? 0.05 times float64 length. Value of type float64 is not used. Let's see. 0.05 times float64 length of e.body. What did I screw up? Value of type float64 is not used. Oh, I forgot my return. Cool. Let's try that again. Okay. So, printing with cost 11 cents. Hello there. Printing with cost $1. I want my money back. Yeah, that looks pretty good. Let's submit it. Up until this point, we haven't really been naming the arguments of our interface's method signatures, but we totally could. So if we take a look at this, this is the copier interface. It's a copy method that it requires, which takes two strings and returns an int. The interesting thing is when you look at this method signature, it's kind of hard to tell what the intention behind the interface is. It's like, great, it takes two strings, but what are those strings supposed to represent, right? So here, we can take a look at what I would consider a better interface definition, where the copier interface actually has a copy method that specifies the source file is kind of the name of the first parameter, and the destination file is the name of the second parameter, and then bytes copied is the integer that's returned. So, you know, the functionality here is identical, but now we have much better, I mean, I would consider it documentation of what the intention behind this interface is. So the question is, are you required to name the arguments of an interface in order for your code to compile properly? No, it'll work fine either way. Next question is, why would you name your interface's methods parameters, right? Like, we don't need to. Why would we do it? Execution speed, memory savings, or readability and clarity. It's going to be for readability and clarity. Type assertions. So type assertions are something you'll see every once in a while. I would argue they're probably not super common, but you will come across them. And the whole purpose of a type assertion is so that you can take an interface and kind of cast it back into its underlying type. So in this code sample here, we can kind of assume that S is an instance of a shape interface. And at this point in the code, because it's just an interface, we don't know necessarily if it's a circle or maybe a square or maybe some other type. So what we do is we do a type assertion to cast it to the circle struct. And basically what happens here is on the left-hand side of the this short declaration operator here, we get back the instance of the circle. So this is going to be an instance of the circle struct, again, the underlying struct behind the shape interface, if it was a circle, right? Because we can't be sure. If we had a shape, we're not sure if it was a circle or maybe something else. But this OK variable, this is going to be a Boolean. And if it's true, then it was a circle and we should have a valid kind of filled out circle struct. If OK is false, then we kind of have to discard the circle because we weren't able to parse out the shape as a circle because it wasn't a circle. So let's move on to the assignment. If it's an email, then it should return the email's to address and the cost of the email. If the expense is an SMS, then it should return the SMS's phone number and cost. If the expense is any other underlying type, just return an empty string and a 0.0 for the cost. Okay, cool. So we've got this get expense report that takes an expense as input. And my guess is, yep, expense is this interface. So our job is to kind of try to cast it into the potential underlying types email and SMS. So first we do email, okay, expense dot, and we'll cast it to an email type, if okay. So if it's an email, return the email's to address. So it's going to be return email dot to address as that string there, and also its cost. So email dot, looks like cost is a method. Email dot cost. Okay. Next we can do s, okay, e dot cast to an SMS. So if it's an SMS, we can return SMS's to phone number, and the SMS dot cost. I believe that's also just, yep, just a method. Okay, and it says otherwise, if it has a different underlying type, return empty string and 0.0 for the cost. Okay, cool. That feels at least like we followed the instructions. Let's see what we get. Not enough arguments in call to SMS.cost. Let's take a look at SMS.cost. Have, want. What did I screw up here? Should be s.cost. I named the struct s. All right, let's try that again. Report the email going to John Doe will cost 11. Email, the SMS. Okay, cool. And invalid expense. Perfect. That feels right. I can come down here and check the test suite. Yeah, invalid. Okay, cool. Let's submit that. When we want to do a lot of successive type assertions in a row, there's actually a better way, and that's with type switches. So here's a syntax for a type switch. Basically, we have an interface, and we cast it at the very top of the switch, and then we can actually check and kind of pattern match against different possible types. If none of the types that we've specified are the matching underlying type, then it will kind of fall down to the default case. So let's write some code and see how it works. Down in the assignment, it says, after submitting our last snippet of code for review, a more experienced gopher, or term for a Go developer, told us to use a type switch instead of successive assertions. Let's make that improvement. Implement the get expense report function using a type switch. Okay, cool. So kind of the same thing though. If it's an email, we'll return a to address and a cost. If it's an SMS, then we should return a phone number and a cost, blah, 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 right? The difference is we're going to use a different syntax this time. Okay, so we're going to be using this switch syntax. So switch value colon equals e dot type. Okay, open brackets, case. We are interested in if the expense is an email. So case email. Now the interesting thing is within this case block, v is an email. So I can treat it like an email. So I can do return v dot, oh, what was it? To address, I think. Yeah. To address v dot cost. Case SMS. Return v dot to phone number, I think it was. To phone number. v dot cost. And default. Return. I think it was empty string, just 0 values, right? Empty string and 0.0. Okay, cool. Let's see what happens with that. Oh, am I forgetting? Nope, I've got... Oh, I'm indenting a little weird. There we go. Let's run that. Cool. The SMS is going to this number with this cost. Got some emails and costs. Okay, that's looking good to me. Now that we've learned what interfaces are and how we use them, let's talk about how we can use them more effective and in a sort of idiomatic and clean way. If you forget all of the other advice that we're going to go over when it comes to writing clean interfaces, don't forget this one, and that is to keep interfaces as small as you can. The best, the cleanest, and the most useful interfaces typically just have 1 or 2 methods defined on them. Imagine a simple stringer interface. It has one method defined on it called string that simply returns a string. You can take that interface and implement it on basically any type, and now you have a super useful interface for logging out string representations of different types. There isn't a hard and fast rule about exactly how many methods you should be defining on your interfaces, but what you really should be doing is looking for kind of the minimal behavior necessary to accurately represent an idea or concept, right? So for example, here's a slightly larger interface from the standard library. Again, normally we'll see interfaces in the standard library with maybe just 1 or 2 or 3 methods. This one has 5, but this is kind of still the minimum amount or the minimal necessary behavior that we need to describe a file, like a file in your file system, right? We need a way to close the file. We need a way to read it. We need a way to seek to individual kind of sections of the file. So this is an example of a slightly larger interface, right? I would say 5 methods is definitely on the larger end, but it's still a good interface because it's using as little behavior as it possibly can to describe an operating system file. So the question that goes along with this is, interfaces should have as blank methods as possible, and the answers are complex, few, and many, and the answer is going to be few. The next mistake that I've seen new Go developers make is when they write an interface that sort of knows about the types that they've intended to satisfy it. So for example, if you have a car interface and you've defined an isFireTruck method on the car interface that returns a bool, whether or not it's a fire truck, that's probably a mistake. You would actually just want to use a type assertion or a type switch if you really needed to figure out the underlying type. You should not make your interfaces aware of the underlying types. This also breaks rule number 1, right? Because rule number 1, we don't need to know if a car is a fire truck for like the minimal behavior of a car. I mean, you can see how this sort of design pattern would get out of hand very quickly because we might need to also define other Booleans like is pickup, is sedan, is tank, right? If you start catering to all of the underlying types of a given interface, your interface is going to be really bloated and become very, very large. So the question here is actually the reverse. It says it's okay for types to be aware of the interfaces that they satisfy. If it were flipped around, the answer would definitely be false. But because we're talking about the types being aware of the interfaces they satisfy, I don't think that's necessarily a problem. They don't need to be aware of them, right? Because again, in Go, interfaces are satisfied implicitly. But I would argue to some extent they are aware of them because the developer had to go, in some cases, out of their way to satisfy the implementation of an interface. So I'm going to go with true on this one. So now this is the reverse question. It says it's okay for interfaces to be aware of the types that satisfy them. No, they should not be aware. Finally, I just want to talk about how interfaces are not classes. Sometimes this can get mixed up, especially if you're coming from an object-oriented background. Interfaces are just a very different idea. Interfaces are not classes. They are much slimmer. Right? Classes have a lot of functionality going on. Inheritance is a fairly complex topic. Interfaces are honestly just a simpler idea. Interfaces don't have constructors or deconstructors that require that data is created or destroyed, right? So that's another way that they differ from classes that have kind of this inherent setup and tear down situation. Interfaces are not hierarchical, right? There's no hierarchical inheritance tree when it comes to interfaces. And the most interesting one is that interfaces define function signatures, but not underlying behavior, right? So this is actually a big difference between interfaces and classes. In a class, a child class can inherit behavior from a parent class, which can kind of dry up your code, right? Don't repeat yourself. In Go, that's not the case at all. An interface doesn't dry up your code. You still have to go implement all of the methods on all of the different types individually. Interfaces just allow us to use all of those types kind of in the same places. Later in this course, we'll get to talk about generics, which is a way to kind of dry up your code and, funny enough, kind of uses interfaces under the hood or kind of as a part of the generics system to make that happen. So finally, the question is, interfaces allow you to define a method's behavior once and use it for many different types. That's false. Go has a very unique way of handling errors. Really quickly, let's review how JavaScript handles errors. And the way JavaScript handles errors is very similar to Python or Java. It uses a try-catch paradigm. And let's contrast that with how Go handles errors in its sort of unique way. Let's pretend that we have a function called getUser. And we'll start with JavaScript. So we have a function called getUser. Whoa. And it returns a user. So we'll do const user equals getUser. And we have to wrap the getUser function, the call to the getUser function, in a try block because we know that the getUser function can throw because let's just say, for example, maybe the user doesn't exist. Okay, cool. So if something goes wrong, we add a catch block, and if this function throws, execution will stop. We'll enter the catch block and do whatever's in here. For now, we can just console.log the error. Now let's take a look at what this function looks like in Go. We do something like this. We do user error := get user. If error does not equal nil, then we could print out the error and return so that we don't continue. And then down here we could, deal with the user object. So use user here. And for consistency's sake, we could say use user here after the user object is created in JavaScript. Okay, so what's the difference? Well, let's talk about the first reason why I prefer Go's error handling to JavaScript's error handling. Let's pretend we need to go get some data for the user after we've already kind of retrieved the user successfully. So let's say we need to go get the user's profile picture. Well, in Go, all we would do is call the next dangerous function. Let's say get user profile, and maybe it takes a user.id as input, right? So we need to successfully wait for the user to come back, and then we can go fetch its profile. All right, so this looks very similar. We're doing another dangerous function, get user profile, and it returns a profile and an error. If an error with the profile occurs, again, we'll just kind of print out the error and return. Otherwise, now we have a profile object. Okay, what would we do in JavaScript? Well, in JavaScript, we can't just take this try-catch and paste it down here and update some stuff. This will not work. If we do get user profile, user.id profile. The problem with this code is that user is only available within this try block. It's scoped to the try block, right? So this user object here will be undefined. So the normal thing to do in JavaScript would just be to take this line here and inject it within the try block, the original try block, right? So now I'm doing my second dangerous function after I do my first dangerous function. The reason I don't like this is that the logic for handling the errors is now all in one place. If I want to handle the error for the getUserProfile function differently or separately, then I want to handle the error from the getUser function, I have to actually nest the whole try-catch like this. Right, so now user.id is accessible because I'm in the same try block, but I get a second catch block. So we kind of get this nasty nesting if we want to treat each individual error separately. And this kind of brings us to the second reason why I prefer Go's error handling, and it's that it forces us to think about each individual error that's passed back from a dangerous function. So again, in JavaScript, kind of the normal thing to do, unless you really needed separate error handling, would be to just kind of do all of your dangerous stuff in one large try block. The problem with this, in my opinion, is that it doesn't encourage me to remember which of these functions is dangerous in the first place. For example, maybe this is a safe function and this is a dangerous function that can potentially throw an error. But looking at this code from kind of a calling perspective, I don't really know that that's the case. Whereas in Go, because a function returns kind of the valid data and the error with every function call, I know for a fact that the getUserProfile function can throw an error because it returns an error value. This will probably make more sense if I actually write out some of these functions. So in JavaScript, the getUser function might look just like this. Function getUser. We could say do some getUser logic here. And then maybe it returns, a user. Looking at the function signature, all I can tell in JavaScript is that this function takes no arguments. And the only way for me to know what it returns is to go find that return statement and see, oh, okay, it returns a user. However, in Go, I actually get two super helpful things in the function signature. And remember, the function signature is just kind of that first line of a function definition. So in Go, if I were to write the function definition for the getUser function, it would be something like this. Func getUser doesn't take any inputs, but it returns let's say a user struct and an error, right? And then we have some kind of do getUser logic here, right? So now, just by looking at this function signature, I can tell that it returns a user and that it could possibly return an error as well that I need to go handle. Whereas again, in JavaScript, not only do I not get to see in the function signature what is potentially returned, but I also don't know that this function can throw. I have to kind of go digging deeper into the function definition to see if there's potentially something dangerous going on in the meat of the function. So again, to reiterate, because this is actually a super important point when you're learning about how errors are handled in Go, the primary reason I like error handling in Go is that it forces me, as I write my code, to be kind of hyper aware of every potential error and make sure that I write code that handles it. So now that we understand what error handling in Go kind of looks like from a high level, let's dive into the details. Errors in Go are just values, and specifically, they're just interfaces. So the built-in error interface is an interface with a single method, the error method, and that method returns a string describing what went wrong. So how do we actually go about handling errors in code? Well, let's take a look at this function right here. So this is a function in the standard library. It's called ASCII to integer. It takes a string and attempts to convert it into an integer value. And potentially that can be problematic, right? Because you can write strings that aren't numbers under the hood. Okay, cool. So what do? We get back an integer and an error. And in essence, it's really simple. The error is either nil or it's not nil. If it is nil, that means everything went fine and nothing went wrong. So if the error is nil, it means there is no kind of string representing what went wrong because nothing went wrong. However, if the error is not nil, that means something did go wrong, right? So if the error is not nil in this case, then we'll print an error message and return from the function, right? So we're basically writing guard clauses that say something went wrong, let's handle this error and get out of here, right? Enough talk, let's write some code so you can see what I mean. Let me expand this so it's a little easier to see the code. Okay, the assignment says, we offer a product that allows businesses that use Textio to send pairs of messages to couples. It's mostly used by flower shops and movie theaters. Okay, great. Complete the send SMS to couple function. So that's this function here. It should send two messages, first to the customer and then to the customer's spouse. So use send SMS to send the message to customer. If an error is encountered, return 0.0 and the error. Do the same for message to spouse. If both messages are sent successfully, return the total cost of the messages added together. Okay, I think I understand what's going on. So we're basically going to send both of these messages one after the other. If any errors happen, we kind of abort early and return the error. Okay, so send SMS takes a message as input. So first we'll say send SMS, and we'll send the message to the customer. And send SMS returns a float64 and error. So we'll say, I think it's the cost. Return the total cost. Okay, yeah. So cost, error, send SMS. All right, if error does not equal nil, so if there was a problem sending the SMS, return 0.0 and the error. So return 0.0. Right? Because this function send SMS to couple returns the total cost and an error. So we're saying if we failed to send the SMS, then it costs nothing and we'll return the error that describes what went wrong. Otherwise, we'll do it for the message to spouse. So we kind of are just going to do this exact same thing. So I'm going to say cost for let's say customer, cost for spouse, and we'll be sending the message to the spouse. Cool. All right, now if we get to the bottom of the function, that means nothing went wrong. So we can return cost for customer plus cost for spouse and nil, right? Because if we get down here, nothing went wrong, so we don't have an error to return. Okay, let's go ahead and run this code and see what we get. And I want to just scroll down and take a look at some of these test cases. Okay, message for customer. Thanks for coming into our flower shop. Message for spouse. We hope you enjoyed your gift. Error. Can't send texts over 25 characters. Okay, cool. So, I mean, if we look at the send SMS function, it actually throws an error, or I shouldn't say throws because we don't throw in Go, right? But returns an error value that says can't send texts over blank characters. So that looks correct to me. Here we've got message to customer, message to spouse, total cost. Okay, this is looking pretty good to me. I'm going to go ahead and submit that. We talked about how error handling in Go is all built around the error interface. In fact, let's just review that really quickly. This error interface is really just an interface that wraps a method returning a string. Because if you think about it, at the end of the day, an error is just a kind of nullable string. Either it's a string representing what went wrong or saying what went wrong, or it's nothing because nothing went wrong. So being good at handling errors in Go has a lot to do with being good at formatting strings or formatting useful error messages. So let's review how we format strings in Go. Most formatting Go is built around kind of these formatting verbs that are defined in the format package, the FMT package of the standard library. So for example, the sprintf function returns a string where it interpolates the values passed into the function after the formatting string into the formatting string where the verbs exist. So for example, this first %v is replaced with name. The second %v is replaced with age. %v is the verb we use for sort of the default format, right? If you format an integer using %v, then it kind of just prints the integer in string form. But there are other ways that we can format stuff. For example, the %f verb is used to format floats. And you can actually specify how many decimal places you want to show up in your output string by kind of prefixing the f portion with a 0.2 for 2 decimal places, or say a 0.1 for a single decimal place. So let's jump right into the coding assignment. Assignment says we need better error logs for our backend developers to help them debug their code. Complete the get SMS error string functions. That's this one right here. It should return a string with this format. Okay, cool. So I'm just going to jump right ahead. So it should return fmt.sprintf, right? Because we're trying to format a string. This format. Let me expand that a little bit. Okay, so return a string with that format. Cost is the cost of the SMS, so I'm going to replace cost here with the cost formatted to 2 decimal places. So %.2f. Right, for 2 decimal places, and replace recipient with the stringified representation of the recipient's phone number, which is this string here. So %v. It's important to point out I could also use s here to format a string, but v and s do the same thing effectively when you're working with strings. And then we need to pass in as parameters the values that we want to format or that we want to interpolate into the string. So it's going to be cost and recipient. I'm going to dedent that because that is some crazy formatting. Okay, that looks better. All right, SMS that costs %.2f to be sent to %v. This looks good to me. All right, I'm going to go ahead and run that and see what we get. Ah, right, can't forget to import the formatting package. Let's run that. Okay, SMS that costs 1.40 to be sent to this string cannot be sent. Awesome. This looks correct to me. I'm going to go ahead and submit that. Let's talk about building our own custom error types. So remember, the error interface is an interface. In fact, let me jump back and show you what it looks like again. So it's just this interface here. And because it's an interface, that means we can build our own types, like this user error struct here, that implement that interface, which means they can be used as errors. And remember that the error interface just has one single method that we need to define, right? The error method that returns a string. And as long as we have that, then our type can be used as an error. So for example, we could create this user error type that stores a name, and then we can use it as an error to format an error message that contains the name of the user's account who had an error. So for example, in this snippet here, we have a send SMS function. And if we're not able to send a message to a user, we can actually just return that user error struct with the user's name. And again, that is an error. We can return that struct as an error type because it implements the error interface. The caller of this function would then just treat it like any other error. The reason this is useful is that we can store structured data within our errors. So if we want to format them a specific way, we have access to sort of dynamic data like a name. Let's write some code that uses this concept. So the assignment says, our users are frequently trying to run custom analytics queries on their message deliverability metrics, right? So we're sending lots of messages. We want to know, are these messages getting delivered? They end up writing a bad query that tries to divide a number by 0. It's become such a problem that we think it would be best to make a specific type of error for dividing by 0. Update the code so that the divide error type, so that's this error type here, or rather this struct here, implements the error interface. Its error method should return a string formatted in the following way: cannot divide dividend by 0. Okay, let's write that method. So it's going to be a function on the divide error type. So I'm going to name it DE, which is a divide error. And the name of the function must be error, takes no arguments, and returns a string. Right? So that's the function signature we need to use to implement the error interface. And then we're going to return a string, and we're going to need to format the string. So we'll use sprintf. The format package is already imported. And this is our template. And dividend, in this case, is a float 64. And it says here, dividend is the actual dividend. Use the %v verb. So %v, okay. So we're just going to kind of do the default formatting for a float 64. And let me indent all this so that it's kind of readable. Where dividend is the actual dividend of the divide error. Okay, so we'll do de dot dividend. That will interpolate there. Okay, that looks correct to me. I think we've implemented the error interface properly. Let's go ahead and run that. Uh-oh, I forgot my comma. This is kind of an interesting quirk of the Go programming language. If you add a new line after the last parameter to a function, you have to put a comma. So this would work. All right, and this would work, but this does not work. All right, that's what I did the first time. So just kind of something to watch out for. Okay, so let's take a look at this. Dividing 10 by 0, cannot divide 10 by 0. Dividing 10 by 2, quotient 5. Dividing 15 by 30, 5. Quotient. Okay, this is looking like it formatted properly. Let's submit that. So we've got a quiz question. It says, what is the underlying type of an error? Is it an interface? Is it a struct? Is it a string? Well, it could technically be a struct or a string, right? Like we saw in the last assignment, but the most correct thing would be to say an interface, because it must always be an interface, right? It must always implement the error interface. It could also be a struct or a string, but it will always be an interface. Next question is, can a type be an error and also fulfill another interface? Well, errors are just interfaces, and we know that types can fulfill any number of interfaces as long as they have all of the required methods. So yeah, there's no problem with this. Let's talk about the errors package. So the standard library in Go has an errors package that exposes a few useful functionalities, but the one we're most interested in right now is the errors.new function. So the useful thing about the errors.new function is it allows us to create a new error from just a string. So we don't need to kind of, define a new struct or a new type and then have it explicitly implement the error interface. That can be a lot of code if all we want to do is kind of return an error with a very specific string. Let's go ahead and use it. The assignment says, Twilio's software architects may have overcomplicated the requirements from the last coding assignment. Yeah. All we needed was a new generic error message that returns the string no dividing by 0 when a user attempts to get us to perform the taboo, right? The taboo of dividing something by 0. Complete the divide function, use the errors.new function to create an error when y equals 0 that reads no dividing by 0. Okay, so this is pretty straightforward. Basically, if y is 0, which means that the number that we divide by would be 0, which is obviously a huge problem in mathematics. You're not allowed to do that in Go or most programming languages that I'm aware of. So we need to return an error here so that this operation never happens. So we'll return errors.new. Looks like the errors package is already imported for us, and we just need to return an error that says no dividing by 0. Okay, let's go ahead and run that and see what we get. Oh, I screwed up. This function returns a float64 and an error, so we should return a 0 value for that first value when we're returning a non-nil error. Let's go ahead and run that. Cool. Dividing 10 by 0, no dividing by 0. All of this looks good to me. Let's talk about loops in Go. So if you are familiar with loops in other languages, loops in Go syntactically are very similar to, say, loops in JavaScript. The main difference is just that we don't use the parentheses around kind of the signature of the for loop, which again is very similar to how if statements in Go work. We're basically just dropping those parentheses syntactically. The initial portion runs at the beginning. So for example, in this snippet of code where we're looping over the integers 0 through 9, in the initial section, we're just initializing a variable I and setting it equal to 0. In the condition section, we're checking and making sure that I is less than 10. So at the end of every kind of iteration of the body, which in this case, we're just printing I in the body, we're going to check and make sure that I is less than 10. If it is, we'll continue on to the next iteration of the loop. Otherwise, we'll be done. And then at the end of every iteration, we'll also be running this after section. So we'll be incrementing I. And that happens before the condition is run. So for example, if we increment I to 10 and then I is no longer less than 10, we will not continue on to the next iteration of the loop, which is why this prints 0 through 9 and not 0 through 10. Let's jump right into the assignment. It says, at Textio, we have a dynamic formula for determining how much a batch of bulk messages costs to send. So we need to complete the bulk send function. It takes a number of messages as input and returns a float64, which it looks like will be the total cost of the batch of messages. Okay, each message costs 1.0 plus an additional fee. The fee structure is, so it's going to be, first message is 1.0 plus 0, so 0 is the fee. Second message is 1.0 plus 0.01. Third message is 1.0 plus 0.02. Okay, cool. And then our job is to use a loop to calculate the total cost of all of these messages for, the number of messages that we've been given. Okay, let's just start writing some code. So total cost, I'm going to just start it out at 0.0, and then we'll use a loop for I : equals 0 to do like num messages iterations. So, a number of iterations equal to num messages. So start I at 0. And then we'll do I is less than num messages and I plus plus. Okay, so this kind of body of the for loop should execute num messages times. And we're going to want to add to the total cost, so plus equals, and we're going to use this formula. So it's going to be 1.0 plus this fee. And how do we calculate that fee? Well, it looks to me like it is 0.01 times basically the message number, right? So for the first message at index 0, I equals 0, it's going to be a fee of 0. So if we just use I, this should work, because if I is 0 and we multiply that by 0.01, anything multiplied by 0 is 0, right? So we'd get 1.0 plus 0. For the second message, I should be 1. So we'll get 1 plus 0.01, because anything multiplied by 1 is itself. And so on and so forth. That's looking correct to me. At the end of the function, we'll just return total cost. Cool, let's run that. Oh, untyped float constant, truncated to int. Okay, so I is an int, and we cannot multiply an int by a float 64, so I'm going to cast I to a float 64. Let's try that again. And take a look at some of these numbers. Okay, cool. So the cost for 10 messages is 10.45. And that sounds about right? Because each message costs 1 plus this like fractional part that grows over time. So like the 10th message would have cost like 0.10, and it would decrease over time. So that looks about right to me. 50 messages. Yep. Okay, I'm going to go ahead and submit that. One interesting thing about for loops in Go is that each section of the for loop, the initial, the condition, and the after, are actually optional, and we can omit any of them. So for example, if we omit the condition, then the for loop will just run forever. So let's see why this might be useful. Let's jump into the assignment. The assignment says complete the max messages function. Given a cost threshold, it should calculate the maximum number of messages that can be sent. And then it looks like the fees for each message are going to be identical to the last assignment. So let's go ahead and just get started. So max messages, we have a threshold, a cost threshold, right? We want to see how many messages we can send while keeping the total cost under the threshold. So I'm going to create a total cost variable and set it equal to 0.0. And then this is going to look really similar to the last assignment, but basically we'll set I equal to 0 to start. I'll skip the condition for now because we don't know to what number we're kind of looping up to, right? We're trying to calculate that. So I don't know where to stop yet. But I do want to increment I with every iteration of the loop. And then I basically want to update the total cost by adding to it and use this formula over here, right? So it's going to be 1.0 plus 0.01 times I, which I need to cast to a float 64. Okay, so that formula is looking, again, identical to last time. Now, if I want to return the maximum messages that I can send while keeping the cost under the threshold, then basically I need to check and say if the total cost is greater than the threshold, then I should return I. Does that sound right? So for example, let's say that right off the bat, the threshold were, I don't know, say -1. Right, so I'm not allowed to send anything. I would want to, in that case, return 0, right, because I can't send any messages. So what would happen? We'd enter the loop. I'd calculate the total cost for the first message, which would be 1.0. And then because the total cost is already higher than the threshold, I would return I, which would be 0. So that works, right? However, if the threshold were a little higher, let's say the threshold were 1.5, then what would happen is we'd do that comparison. The total cost would be less than the threshold. So we'd continue to the next loop, iteration of the loop, where I would be incremented to 1. And then on that next iteration, we'd go over. Okay, so this is looking good to me. Let me go ahead and run this code. Okay, so with a threshold of 10, I can send 9 messages without going over the threshold. That sounds right, right? Because I'd have like 9 in some fractional part. Let's go ahead and submit it and see. Most programming languages have support for a while loop. And really a while loop is very similar to a for loop, except it doesn't have that kind of initial and after statement. It just runs until some condition is no longer true. Now, because of this similarity, the authors of the Go programming language decided to not include an explicit while loop with a while keyword. Instead, the for loop is a while loop where just basically both those side kind of sections are omitted, and we just have a condition that follows the for keyword. So in other words, if we have a for keyword and then a single expression, then it is a condition that while true will continue to kind of run the body of the loop over and over and over again until the condition stops being true. Let's take a look at an example. Here we have a variable called plant height. We start it equal to 1, and we've done this outside of the for loop, right? And then within the for loop, we just have one section where we're comparing the variable plant height to the number 5. Right? And while it is less than 5, we'll print this message, and then at the end of the loop, we'll increment plant height. Now, you might notice this looks just like a for loop where we've essentially taken the initial statement and moved it up outside of the for loop body, and we've taken the after statement and moved it within the for loop body, and that is what we've done, right? But it's to demonstrate that this is valid syntax. Let's jump right into the assignment. Okay, so the assignment says we have an interesting new cost structure for our SMS vendor. So at Textio, we have a vendor that we have to pay to send text messages through, right? So we're a software service that makes sending text messages easy, but we do have to pay some kind of maybe hardware service that actually does the sending of the text messages kind of over the wireless network. Okay, they charge exponentially more money for each consecutive text we send. Let's write a function that can calculate how many messages we can send in a given batch, given a cost multiplier and a max cost in pennies. Okay, so given a cost multiplier and a maximum cost, our function will return basically the number of messages that we're allowed to send that's under that max cost. So it says, in a nutshell, the first message costs 1 penny. Okay, actual cost in pennies starts at 1. And each message after that first message costs the same as the previous message multiplied by the cost multiplier. Okay, so that's happening here. Gets expensive. There is an infinite loop in the code. Okay, so on line 10 here, we have this for with no body and then an open curly bracket. Let me show you what happens when we run that. Our code's going to sit and run and execute the body of that for loop over and over and over and over with no exit condition. This is obviously a problem. We don't want an infinite for loop there. So our job is to exit before incrementing max messages to send if the cost of the next message would go over the max cost. So all we need to do is check and only execute this loop while the actual cost is less than or equal to the max cost in pennies. And we're going to have to cast, looks like, so this is a float, this is an int, so we're going to cast this to float 64. Now, this should work because max messages to send starts at 0. So assuming the actual cost is less than the max cost, then we go ahead and increment. Say we can send one more message, and then we take a look at the next cost. And if the next cost is still less, then we'll essentially get to add another message. So we'll keep kind of looking ahead and calculating the next cost, right? And as soon as the next cost goes too high, we stop. Okay, so I'm gonna go ahead and run that. Cool. So with a multiplier of 1.1 and a max cost of 5, we can send 17 messages. That sounds about right. Right? The actual cost starts at 1. The max cost is 5. Multiplier of 1.1. Yeah, that sounds right. So the multiplier goes up. Max cost goes up. Now we can send 9 messages. That all looks good to me. Let's talk about the modulo operator, how it works in Go, and kind of how it works generally. So the modulo operator is a % sign. So it looks like this, right? And the modulo operator essentially calculates remainders. So what do I mean by that? Well, let's jump into an example. Let me switch colors. So 4 divided by 3 in sort of a normal floating point division equals like 1.33333 forever, right? We have this fractional part. However, That's how math works normally, and that's how math works in floating point division in a language like Go. If we're doing integer division, then we can't have a floating point result. So the result of 4 divided by 3 in integer division is actually just 1. It's essentially the number of times that 3 can be divided evenly into 4, and then we chop off the remainder. The interesting thing about the modulo operator is that 4 modulo 3 doesn't return the number of times that 3 can be divided evenly into 4. It returns the remainder after that division. So actually, in the case of 4 modulo 3, the remainder is also 1. So it's the same. But, for example, 5 modulo 3 is 2. And 6 modulo 3 is 0 again, because 3 divides evenly into 6, right? 6 integer division by 3 is 2, right? Because 3 goes evenly into 6 twice, but the remainder is 0. That's why 6 mod 3 is 0. Let's just do a couple more examples. Feel free to pause the video in between when I give the question and provide the solution so that maybe you can practice a little bit. Okay, so let's do 12 mod 4. We'll do, in fact, maybe I'll just write out all of the problems first. Let's do 16 mod 5. Let's do 22 mod 8. And let's do 27 mod 6. I think those will be good. Okay, 12 mod 4. So does 4 divide evenly into 12? Yes, 4 times 3 is 12, right? So the remainder is 0. All right, how many times does 5 divide evenly into 16? The answer is 3, right? 5, 10, 15. And the remainder would then be 1. How many times does 8 go into 22? 8, 16, 24. So 24 doesn't work, so it's going to be 16. And then 22 subtract 16 is 6 is the remainder. Right? And then 27 mod 6. 6 goes into 27 4 times. 6 times 4 is 24. So a remainder of 3. So an important thing to note here is if you're trying to figure out if a number divides evenly into another number, then you can just check if, say, A mod B equals 0, right? If A mod B equals 0, then that means B divides into A an even number of times. So A is a multiple of B. So in Go, the modulo operator is just that percent sign, right? So 7 mod 3, this expression is going to evaluate to 1. We'll also need to know about the logical AND operator and the logical OR operator, which are double ampersand and double bar respectively. The logical AND operator operates on 2 Boolean values and only returns true if both sides are true, right? This and that. The OR operator just needs at least one side to be true, right? In order for the entire expression to evaluate to true. Let's jump into the assignment. It says we're hiring engineers at Textio, so it's time to brush up on the classic FizzBuzz game. Coding exercises have been dramatically overused in coding interviews around the world. Complete the FizzBuzz function that prints the numbers 1 to 100 inclusive, each on their own line, but substitutes multiples of 3 for the text fizz, multiples of 5 for buzz, and multiples of 3 and 5 for FizzBuzz. Okay, so we do a for loop. For I colon equals 0, I is less than 100, actually less than or equal to because it's set inclusive, right? I plus plus. Okay, we need to think about the order in which kind of these things can happen. So we're checking for multiples of 3, multiples of 5, and multiples of 3 and 5. So we actually should check for multiples of 3 and 5 first, because something could be that and one of the other two conditions, right? It could be a multiple of 3 and 5 and just a multiple of 3. That makes sense. Maybe it'll make sense when I type it out. So if I mod 3 is 0 and I mod 3 is 0. Oops, not 3 and 3. 3 and 5. Then we'll print fizzbuzz, right? Else if I mod 3, 0, then we'll just print fizz. Else if I mod 5 is 0, we'll just print buzz. Otherwise, we'll print I, right? If they're both multiples, fizz buzz. If it's just 3, fizz. If it's just 5, buzz. Okay, let's try that. Oh, cannot forget to import the formatting package. Okay. Let's see. Fizz buzz. 1, 2, fizz, 4, buzz. 5, fizz, 7, 8. Fizz buzz, 1. Oh, haha. 1 through 100. That would have been close. I almost didn't follow instructions. I was like, why do we have a fizz buzz up front? That doesn't make sense. Okay, cool. So 1, 2, fizz, 4, buzz, right? 5 is a multiple of 5. 10 is a multiple of 5. 15 is a multiple of 5 and 3. So this is looking correct to me. I'm going to go ahead and submit that. So in the last assignment, we kind of did a if-else chain within our for loop, but there's another way that we can write guard clauses within loops so that we don't have to necessarily do that if-else chaining if we don't want to. The continue keyword stops the current iteration of a loop and continues to the next iteration. So continue is a powerful way to use guard clauses, right? So we write our for loop, and then if some condition happens, we can kind of bail out of the body of the for loop early and just continue on to the next iteration. The break keyword is similar in that it stops the current iteration, but instead of continuing on to the next iteration, it just ends the loop entirely. Moving on to the assignment. It says, as an Easter egg, we decided to reward our users with a free text message if they send a prime number of text messages this year, because Textio is run by a bunch of nerds. Complete the print primes function. It should print all of the prime numbers up to and including max. It should skip any numbers that are not prime. Okay, so here's the pseudocode. Print primes max. So let's convert this pseudocode into real Go code. So for n in range 2 to max plus 1. So we're going to do for n colon equals 2. N is less than max plus 1. N plus plus. Okay. If n is 2, n is prime, print it. fmt.println n. And we need to continue, right? Continue the next iteration. We're basically saying, okay, this n is prime, we'll print it, and then we can move on. All right, if n is even, so if n mod 2 is 0, right? That's an easy way to check if something is even and not make your way onto R programmer humor. If n mod 2 is 0, n is not prime, skip to the next n. So we do not print and we just skip. Okay. Next, we do a nested for loop here for I in range. So for I colon equals 3 to the square root of n plus 1. Okay, this is actually interesting. I could use the math.square root function here. That would be a valid way. But if I want to stay in integer land, which I think I do, I can do, I can instead square I. So I times I, and see if it's less than n plus 1, right? Does that make sense? So instead of doing I is less than the square root of n, I can do I squared is less than n. Right? That makes sense to me. Cool. Because basically we're just saying we only need to check up to the square root of n. We know that if we go higher than that, but like, we don't care about numbers higher than the square root. Cool. Next one is I plus plus. If I could be multiplied into n. So if n mod I. Oops. If I goes into n evenly, so if that results in a 0, n is not prime, skip to the next n. Okay, so I can't continue here, because if I continue here, I'll just skip to the next I, and I want to skip to the next n. So I think what I do here is I do something like is prime true. Here I set is prime is false and break. And then at the end of the for loop, I can say if not is prime, continue. Okay. Okay. If n is not prime, skip to next n. Yeah. So we'll break out of this loop. Right? We'll break out of this loop. And then we'll continue. Cool. Now, I just want to be clear. There are other ways to write this function. I'm kind of, on purpose, using lots of continues and breaks so that we can get some practice with it. Cool. N is prime printed. So if we get all the way to here without any of these kind of guard clauses being triggered, then n is just prime. So fmt.println n. Let's run that and just sanity check our code. Prime's up to 10. 2, 3, 5, 7. Yep, right? That's 2 is a prime number. It's kind of like the only even prime number. And 9 is an odd number before 10, but it's not prime because it's evenly divided into by 3, right? Maybe I should have even explained what prime numbers are in the first place in case you're not familiar. There is a link here if you want to go read more about them, but basically a prime number is any number where the numbers that multiply evenly into it are anything except 1 in itself. So if it has any multiples, or if it has anything that multiplies into it that isn't just 1 and itself, it's prime, right? So 7, you can't multiply 2 into 7, you can't multiply 3 into 7, you can't multiply 4 into 7, right? So it's prime. Let's just look at a couple more of the examples. So up to 20, we got 2, 3, 5, 7, 11, 13, 17, 19, right? Again, we're skipping 15 because it has the multiples 3 and 5. Prime's up to 30, again, skipping 25, and also skipping 27 because 9 divides evenly into 27 as does 3. Cool. So hopefully that makes a bit of sense. And then just kind of as an explanation of why this pseudocode works, we're skipping even numbers because they can't be prime, right? If 2 divides into something, it's not prime. We only check up to the square root because anything higher than the square root has no chance of multiplying evenly into n, right? So like, for example, take the number 16. Its square root is 4. Nothing over 4 could possibly evenly divide into 16 that the square root couldn't, right? So like, for example, 8 divides evenly into 16, but that's only because 4 and 2 already do. Okay, we start checking at 2 because 1 is not prime. 1's kind of a special case number. Okay, so this is looking correct to me. I'm going to go ahead and submit it. Let's talk a little bit about how arrays work under the hood. So if you're familiar with the idea of arrays from JavaScript or lists from Python, arrays in Go are similar. You can think of an array as just an ordered list of items. So we usually denote arrays with square brackets, and an array of, say, 3 integers might be something like 2, 3, 1, right? So we've got 3 integers stored in our array. The first thing is the integer 2. It's stored at index 0. The next one is a 3. It's stored at index 1. And finally, we have a 1 stored at index 2. Now, here's the big difference between arrays in Go and arrays in JavaScript or lists in Python. In Go, arrays have a fixed size. So the type of this array would be 3 int. Okay. So inside of the square brackets, we kind of indicate the size of the array, and then after we indicate the type of thing in the array. So this array's type is an array of 3 integers. In languages like JavaScript, or again, like lists in Python, arrays are kind of dynamically resized. They don't have a fixed size. You can add things onto the end, you can push stuff onto the beginning, but in Go, arrays are always fixed. So to show you what this looks like in code, basically we can create a new array of 10 integers, like this. It will initialize all of the indices in the array to the 0 value. So this would be an array of 10 zeros, basically. If we know what we want to store at each index in the array, then we can use an initialized literal here. So we're saying we have an array of 6 integers, and in the first index, I want a 2, and then a 3, and then a 5, and so on. So let's jump into an assignment and see how this works. The assignment says, when a message is not responded to, we allow our clients to have up to 2 additional messages that are sent as nudging reminders. Get message with retries returns an array of 3 strings where index 0 is the first message. If the first message is not answered by the recipient, we send the second, and then we'd send the third. Update get message with retries to return the 3 following strings in an array. Click here to sign up. Pretty please click here. We beg you to sign up. Okay, cool. So this is pretty straightforward. Here we're just going to return an array, and you can see the return type up here. It's a string array of size 3. So we just need to create an array literal and return it. And in this case, we want an array of strings of size 3. So array string size 3. And we can use these curly brackets to be kind of where we put the string literal. So the first string is going to be click here to sign up, right? This is the first message that's sent. Pretty please click here. And we beg you to sign up. And then just remember that in Go, you do have to put that last comma if you're going to use a new line. Okay, pretty straightforward, right? Let's see how that works. Sending to Bob, click here to sign up, they responded. Sending to Alice, click here to sign up, pretty please click here, they responded. Okay, this is looking good to me. Gonna kind of get a peek at the test suite. Cool, let's submit it and see how we did. So we've talked about how arrays are fixed in size, and you might be wondering, well, that's not very useful. Why would I care about an ordered list of things if I can't even add to or remove from the list? Well, that's where slices come into play. So let's draw out a simple array. I'll do it in yellow. Let's just say it's storing some numbers. So we might have some numbers like 6, 3, 2, 6, 5. And I'll draw the indices. Let's do that in pink. So the index of the first item is 0, and then 1, 2, 3, 4, right? And the size of the array is 5, which in Go, we would write like this. We would say we have an array of 5 items, and they are integers. Okay, cool. So we understand what an array is, but what's a slice? Well, slices in Go are written with this syntax. Open close bracket, int. And you'll notice that the size is missing. Okay, so a slice is a dynamically sized, flexible view into an array. So slices are built on top of arrays. So that means, for example, that I could create a slice that just looks at this kind of middle portion of this array. If I were to write this in code, I would basically say if this array is named A, so A is this yellow array here, if I want to create a slice on top of that array, then I could write B : equals A from, we're using square brackets here, index 1 up to, but not including, index 4. Okay, so the first number is inclusive, the second number is exclusive. And now B is this slice of kind of just that middle view of the array. And here's the important thing to understand. In Go, we actually almost never deal with arrays directly. 99 times out of 100, you'll just be working with slices because slices provide a much better developer experience. They're built on top of arrays for kind of memory management reasons, which we'll talk about in just a second. But you really want to be working, for the most part, with slices because you don't have to worry about that fixed size problem. So just to review slices sort of in code, we can create an array literal like this, right? This is an array because we have the size of the array there, 6 integers. And then we can create a slice on top of the array like this. Cool. Let's jump into the assignment so you can kind of get a feel for how this all works. Okay. The assignment says, retries are a premium feature now. Textio's free users only get 1 retry message, while pro members get an unlimited amount. Complete the get message with retries for plan function. It takes a plan variable as input. That's a string, matches up to one of these. If the plan is a pro plan, return all of the strings from get message with retries. Okay, cool. So get message with retries, it looks like returns an array of 3 strings. Okay, let's just jump right into it. If plan is plan pro, then we'll return all messages, right? Return all the strings, yep. And a nil error. Otherwise, if the plan is plan free, return the first 2 strings, right? The original string and kind of the first retry message. So return all messages, and we're going to slice it from index 0 up to, but not including index 2. So it'll be indexes 0 and 1, right? Two strings. And then we'll also return nil. And finally, if it's neither of those, return an error that says unsupported plan. So return nil errors.new unsupported plan. And nil is just kind of the 0 value of a slice. Cool. This is looking good. We need to make sure we import the errors package. Let's go ahead and run this and see what happens. Oof, we got an error. Cannot use all messages, variable of type array size 3 string as slice of string. Okay, cool. So we have an array. All messages is an array, not a slice, right? So we actually need to slice this to change its type, but we want all of the values inside of the array. So we're just going to use this colon syntax to get access to everything in the underlying array. Let's run that again. Cool. Sending to Oscar. Click here to sign up. Pretty please click here. So that's two messages with no response. And I'm guessing because, yep, Oscar's on a free plan. Jeff is on a pro plan, so he gets all 3 messages. This is looking correct to me. These next few questions will reference kind of excerpts from the Effective Go book, which is definitely a book I recommend reading, although it is a bit out of date. It was written a while ago, and the authors have basically made the decision not to update the book over time, kind of keeping it as a snapshot. So it has a lot of great stuff in there, and Go has very strong backwards compatibility, so it's still a great read. Just kind of be aware that it hasn't been updated in a while. Cool. That said, everything we explained here, I'll obviously provide context for. So the thing that's important to understand in this section is that slices are references to kind of what goes on underneath the hood with arrays. So what that really means to you as a developer is when you use slices, and more specifically when you pass them around, say, into a function, you're actually passing a reference, which means if you change the values in that slice within a function, the caller, the person who called your function, or I should say the bit of code that called your function, will actually have access to those changes. It will see those changes even if you don't explicitly return the slice again. Now, this is different from sort of normal primitive values, which are passed by value. You might remember us talking about pass by value earlier in the course. Typically, if you pass in, say, a string or an integer into a function, and then within that function you change it, the caller won't see those changes. You have your own copy of that data. That does not hold true with slices. So just understand that when you pass a slice into a function, it might get modified. Okay, cool. So which references the other is the question. Do arrays reference slices or do slices reference arrays? And the answer is that slices reference arrays. The next question is, can multiple slices point to the same array? Right? Is that true or false? Multiple slices point to the same array. That is true. Remember, slices are just kind of a view into an array. So it makes sense that you can have multiple views into the same underlying array. So multiple slices can point to the same array. Now, here's that question that we talked about earlier. A function that only has access to a slice can modify the underlying array. The answer to this is that is true. Even if the function doesn't return that slice, it can modify the values in the underlying array. Let's talk about how slices work, kind of specifically how they work in relation to your computer's hardware or your computer's RAM. Now, RAM just stands for random access memory. It's where variables are stored. The best way to think about RAM is just a mapping of addresses, so address, to data, right? It gives us a place to store stuff. So for example, at address 0, we might have some data that represents, I don't know, the number 4, right? And then at address 1, we might have some data representing the number 5. I don't know. I'm just making stuff up. But you get the idea. We have addresses and we have data associated with that address. Slices and the arrays that they are built on top of are stored in contiguous memory. Basically, what that means is a slice or an array is an address in memory where the slice or array starts. So for example, at address 0, we might say this is the start of a slice. And the slice actually continues for the next, several kind of bytes of data. Let's say that it's a slice of length 3, so it actually would reach across all 3 of these addresses. So if you have an array or a slice, and its address is 0 and its length is 3, then you know kind of how many stores of data in memory your slice or array will use. Now, this is primarily important for performance. Because all of the data is stored next to each other in memory, it's going to be faster to kind of iterate over all of the values in our slice. If we stored each index in kind of random places in memory, it would take a lot longer to go collect all of that data just, from a hardware perspective. However, there is a downside to having to store all of our memory kind of next to each other. Let's pretend that we have this slice or this array that starts at address 0 and has a length of 3. So it's using kind of these 3 addresses in memory, or these 3 bytes of memory. And let's say here at address 3, we're storing a different value. Maybe we're just storing, I don't know, the number 6, but this is a different variable. This is some other variable. The problem is, if we want to expand our slice, say add another value to it, we're going to run into the next thing in physical memory. That's a huge problem. We don't want to overwrite some other variable just because we're growing our slice. So this is why arrays are fixed in size. If we just can't grow them, then we'll never have this overwriting problem. So the question, of course, is how do slices do it, right? Well, slices are built on top of arrays. And basically what happens is, I can draw this out for us. When we want to grow a slice whose underlying array has run out of room, right? So we have our slice built on top of this length 3 array, and we want to grow it into a length of 4. What happens under the hood, and this all kind of happens without you seeing it as a developer. You'll see later when we get to the syntax, it's actually really simple. What happens is this data is copied into a new location in memory. So we just take this 4, we put it over here, 5 over here. Actually, I'm going to use the same colors. That would probably be easier to understand. So 4 comes over here, 5 comes over here, 3 comes over here. And then let's say that we know we want to grow our slice significantly. So the new underlying array, let's say, will have a length of 6 now. So it had 3 here, Now the new array has pre-allocated, right? We've essentially reserved memory for up to 6 spaces. Let me draw all of that out. Cool. And these addresses over here are going to be totally different, right? Maybe it's address 15, address 16, 17, 18, 19, and 20. Cool. So all the data from the old array gets copied over, and now we're able to expand our slice to a length of 4. Right, so here our slice was length 3 and the underlying array was length 3. Now we've copied over the data. We've created a much larger underlying array, and now we have a slice of length 4. Maybe we wanted to append, say, the number 2 to the end of the slice. So again, as the developer, you're not going to have to do all of this array management manually, but it's important to understand that this is what's going on under the hood because it has performance implications. Copying data isn't super efficient. If you're copying data from one section in memory to another over and over and over again, it can slow down your programs. So now that we've covered all of that memory stuff and how it works under the hood, what does that mean in code, right? Well, this is how we can create a slice without explicitly creating an array under the hood, right? So this will automatically create an array under the hood for us if we use this syntax. So this is basically saying, I want a new slice of integers. I want its initial length to be 5. So the length of the slice, right? The length of the view into the array will be 5. And the capacity will be 10. So the capacity is kind of the total space that we have to grow the slice until we need to allocate a new array under the hood. So you could almost think of this capacity as just the length of the underlying array. Now, I told you that you don't need to think about the size of the underlying array, and that is true. Typically, you'll actually use this syntax where you don't even specify a capacity. So if you do not specify a capacity, it defaults to the length. So the kind of length of the underlying array for a slice of integers with length 5 will just be 5. And if you grow it past that, the memory copying will happen and you'll create a new underlying array. Now, you might be thinking, oh, that's terrible for performance. In reality, it's not that bad. The only reason you would start to kind of futz with specific capacities and optimizing your memory copying is if you're having performance problems. Generally speaking, the convenience of keeping your code simple and easy to understand is going to outweigh kind of the performance cost that it'll have. It's a very small one, generally speaking. And then it's also just worth pointing out that we can also create slice literals, right? So this just creates a new slice of length 3 and initializes these 3 values into that slice rather than what would happen up here, which is that we create kind of all of the 0 values to fill out the slice kind of the given length. So this would be a slice of 5 zeros, right? And then to just point out 2 more things regarding syntax, there is a built-in length function that returns the length of a slice and a built-in cap function that returns the capacity. So now that we are experts on slices, let's jump into the assignment. It says, we send a lot of text messages at Textio and our API is getting slow and unresponsive. So I just mentioned how you probably shouldn't worry about performance. Well, here's a case where you should worry about performance, right? You shouldn't worry about performance until, well, it starts to become a problem. So we're starting to have a problem with this memory copying being slow. So we've been asked to pre-allocate our slices. It says, if we know the rough size of the slice before we fill it up, we can make our program faster by creating the slice with that size ahead of time. All right, so complete the get message costs function. It takes a slice of messages and returns a slice of message costs, float 64s, right? Reallocate a slice for the message cost with the same length as the message slice. Let's go ahead and start off with that. So costs, we'll make a new slice, and it's going to be a slice of float 64 and a length of length messages, right? Same length. Cool. Now we want to fill the cost slice with cost for each message. So let's go ahead and iterate over each message. So for I : = 0, I is less than length of messages, I ++. Let's get the message at that index, messages at 0. Oh, not a 0. Excuse me. At I. Okay, the cost in the cost slice should correspond to the message in the message slice at the same index. The cost of a message is the length of the message multiplied by 0.01. So cost equals the length of the message multiplied by 0.01. That's going to need to be cast to a float 64. Perfect. Cool. And then we just need to save that into the costs slice. So costs at I equals cost. Right? Correspond with the same index. And we know that that index already exists because we pre-allocated it to the correct size. Cool. So now we can just return costs. Let's go ahead and run that. And see if these make sense. Okay, these costs line